Can you explain what happens in this demonstration? Why does the tray fly across the table? Why do the cardboard cylinders go with it? Why do the eggs drop straight down into the water below? Watch as we set up the demonstration so that you can repeat it in your classroom. Notice that the tray extends about 10 centimeters over the side of the table. Make sure that the cardboard cylinders are placed directly over the middle of the beakers of water. And it might be a good idea to use boiled eggs in case anything goes wrong. Use a broom with stiff bristles and stand on the brush part as you pull the handle back. Then let it go. Watch what happens again in slow motion.
By the end of this lesson, you should be able to answer each of the questions you were asked about the demonstration you just saw. In addition, you should be able to explain why seatbelts are necessary and why you feel pulled to the right when your car turns left. Explanations of these and many other natural phenomena are based on this unit's topic, Newton's laws of motion.
During this lesson, you will state Newton's first and second laws of motion, define inertia and force, and give examples of Newton's first law in everyday life.
Before we talk about Isaac Newton, we need to get some historical perspective on what great minds thought about motion prior to his work. Let's start with Aristotle. Now, don't take any notes on what he taught, because it all turned out to be wrong. And since so many people, including the Catholic Church in Rome, believed whatever Aristotle said to be absolute truth, he retarded the growth of science for hundreds of years. Aristotle divided motion into two kinds: natural motion and violent motion. It was natural for heavenly bodies, such as planets and stars, to move in perfect circles around the Earth. After all, the Earth was considered to be the center of the universe. For very light substances, like smoke, it was natural to move straight up, towards the heavens. But most objects would seek their natural resting places on the ground, close to the center of the Earth. That's why falling was considered to be a natural motion. Now, on the other hand, violent motion was motion forced on an object.
The early Greeks believed that vertical motion was natural, while horizontal movement was forced. This is because a stone will fall vertically with no outside force appearing to be applied to it. Well, if one wanted the stone to travel horizontally, a force such as the muscular force of the arm had to be exerted on it.
Since horizontal motion was not thought to be natural, there had to be some cause, a push or a pull. A ball moves horizontally through the air because of the force exerted on it by a thrower's arm. A ship moves because the wind pushes it, just like the carriage moves because the horse pulls it. For nearly 2,000 years, it was accepted that if an object was moving against nature, it was because some force was acting on it. Without a force, there could be no motion, because the object was in its natural place. And since the Earth's natural place was at the center of the universe, and no huge force was pushing or pulling it, it was just common sense to believe that the Earth did not move. And then, a Polish monk looked into the heavens and, based on his observations, decided that the Earth must move around the sun. You can imagine how popular this idea was at the time. In fact, Copernicus did his writing in secret and only sent his ideas to a printer in the last days of his life. To Aristotelians, the idea of the Earth hurtling through space was unthinkable. Here's why. When an apple falls from a tree, why should it land directly beneath the limb of the tree? If Copernicus was correct, wouldn't the tree and Earth leave the apple behind, making the apple land miles away? It was Galileo who defended the ideas of Copernicus. He did it with his own observations of the heavens using the telescope he invented and through scientific experimentation and creative thinking. Watch this and be ready to tell what ideal conditions Galileo imagined in his inclined plane experiment. Unlike Aristotle, Galileo did experiments to support his ideas. He repeatedly observed and timed balls rolling down one inclined plane and up another, and found that the ball always gained its original height. If the second plane was shallower, the ball rolled farther until it reached its original height again. The more shallow the second incline, the farther the ball rolled, trying to reach its original height. Galileo concluded that on a perfectly horizontal plane, with a perfectly smooth surface, the ball would keep on rolling forever. For his study of falling objects, Galileo imagined ideal conditions without air. In his study of horizontal motion, the ideal condition he imagined for the inclined plane was the absence of what? Did you say friction? That's right. Without friction to slow the ball down, Galileo imagined that it would continue moving forever. He said that it was not the ball's nature to come to rest, as Aristotle had claimed, but that a property of matter, which he called inertia, would resist any change in the object's motion. The word inertia comes from the Latin word for lazy, or inert. Galileo said that it was not the nature of the earth to come to rest, but that its inertia would keep it moving. No force was necessary to keep it in motion, and objects on the earth would continue to move with it, not fly off. We'll learn more about that later. For now, we need to get back to the story of Galileo. It seems that in addition to his experimenting, he did a great deal of talking and writing, basically treating Aristotelians as fools. And this got him in trouble with the church officials in Rome. Galileo was put on trial in 1634 as part of the Inquisition. Because he feared torture or execution, he publicly recanted his Copernican views that the earth moved around the sun. He was sentenced to house arrest and spent the last 8 years of his life confined to his estate near Florence. But Galileo's mind and pen would not be stopped. During his confinement, he wrote his most important work. It was smuggled out of Italy to France and published in Holland in 1638. This work became cornerstone of the study of mechanics. Galileo died in 1642. It was not until 1984 that the Church admitted that it was wrong and Galileo was right. Isaac Newton was born in England within a year of the death of Galileo. Just as I'm sure you do very productive schoolwork when you are stuck at home on snow days, Newton did some of his best academic work during the plague years when he left Cambridge University. He spent that time at his family's farm that just happened to have, well, you guessed it, an apple orchard.
At the age of only 23, Newton wrote his 3 laws of motion. His work goes beyond Galileo's description of motion to explain the reasons for that motion.
Isaac Newton is known as the most influential scientist of modern times, but he gave credit to those who went before him. His famous quote, "If I have seen farther than others, it is because I have stood on the shoulders of giants," surely referred to the work of Galileo. In fact, Newton's first law of motion simply restates Galileo's original idea. He even uses the term inertia, which Galileo used first. In fact, Newton's first law is often called the law of inertia.
Newton's first law of motion is also called the law of inertia. It states that when no net force acts on an object, the object will either remain at rest or remain in uniform motion. In other words, objects at rest tend to stay at rest, and objects in motion tend to stay in motion at constant speed and in a straight line. Unless some outside force pushes or pulls the object, it will remain in its present state of rest or uniform motion forever.
The 2 most important terms involved in this law are inertia and force. Let's talk about them one at a time. Inertia may be a term that is new to many of you. It is a property of matter, just like color, temperature, and volume are properties that you can observe or measure. Inertia is a property of matter that resists changes in its motion. how do we measure inertia? Well, the best measure of an object's inertia is mass. The more matter an object has, the more mass it has. And the more sluggish or resistant to changes in its motion it will be. Now don't confuse mass with weight. Remember that mass does not depend on gravity. It would be easier to lift this barbell on the moon because lifting involves opposing the force of gravity, which is less on the moon. But it would be just as difficult to shake this barbell on the moon or in space as it is on Earth.
A force is a push or pull. Only net forces actually result in changing motion. Remember that forces are vectors, so direction is important. Look at this book. There are two forces acting on it. The weight of the book is the force of gravity pulling down on the book, but the table is supporting the book. That means it is pushing upward on the book. Since the two forces are equal, the net force on the book is 0, and the book will remain at rest.
Examples of the law of inertia are all around you. What happens to your head when a car suddenly moves forward? It feels like your head snaps backwards, but an observer outside the car would see the car accelerate forward and your head remain at rest. The inertia of your head resists any change in motion. Now, watch what happens when a car stops suddenly.
Newton's first law of motion explains why the use of automobile seat belts is critical to passenger safety. If a car stops suddenly, unrestrained passengers continue to move forward until they make contact with the windshield, steering column, or dashboard. Most injuries in automobile accidents are caused by the passengers remaining in motion until smashing into the dashboard or steering wheel. If, however, passengers are restrained by seat belts or airbags, their motion becomes nearly equivalent to that of the vehicle, and the vehicle, rather than the passengers, absorb the majority of the collision's force.
Imagine this. You are in the passenger seat of a convertible that turns sharply to the left. What do you experience? It feels like you are being pulled toward the right. With no seatbelt, you actually could slam into the door. But what would an observer on a platform above your car see? He would see the car turning and your body continuing to move in a straight line. Inertia resists any form of acceleration, including changing direction. Now it's your turn to come up with some examples of Newton's first law in your everyday life. Your teacher will turn off the tape and give you some time to think of some situations and share them with your class. Then we'll be back. Here are some examples of Newton's first law of motion.
When you use one hand to rip off a paper towel from a full roll, the inertia of the full roll resists moving and it will stay put. But try the same thing with a half full roll and the whole thing will come with you. It has less inertia.
To tighten the head of a hammer on its handle, we bring the hammer down quickly and then stop it suddenly on a hard surface. The inertia of the massive head keeps it in motion after the handle is stopped.
Float a toy boat in a bowl of water. When you turn the bowl, the water and boat don't turn. Inertia resists the change in direction.
Here's a good one. If you use heavy plates, with lots of inertia, you can pull a tablecloth out from under them. Make sure that there's no hem on the cloth and pull quickly in a horizontal direction only. Here goes.
Now you should be able to answer the questions about the egg drop demonstration we showed you at the beginning of this program. Take another look and then your teacher will pause the tape and give you a chance to answer the questions. In your answers, try to use the terms we've learned during this lesson.
Can you explain what happens in this demonstration? Why does the tray fly across the table? Why do the cardboard cylinders go with it? Why do the eggs drop straight down into the water below?
First, why does the tray fly across the table? You should have said that a force was applied to the tray, causing it to start moving. We used the broom handle so that this force would be horizontal. The cardboard rolls went with the tray because they are very light and don't have much mass, or inertia. So they were not able to resist the force exerted on the tray, and because of friction, on them too. Now, the eggs have lots of inertia, and were able to resist moving with the tray and cardboard rolls. They remained at rest until the net force of gravity pulled them down. How did you do? I hope this program made it easier to answer the questions.
Here's a physics challenge for you. Your friend says that he doesn't believe that objects in motion tend to stay in motion because even on a smooth, flat road, he has to keep giving his car gas or it will slow down and stop. How do you explain to him that the law of inertia still applies? Tell your teacher.
Remember that Newton's first law applies when there is no net force acting on the object. It would be easier to explain this to your friend if you had this apparatus. Watch what happens when I give this plastic puck a push across the table. It slows down and stops. Now, watch what happens when I let this balloon furnish air for the puck to slide on. It just keeps on going. What's the difference? Did you think of friction? With the first puck, the force of friction acted on the puck to slow it down. With the air from the balloon, we eliminated most of the friction, so the puck's inertia could keep it in uniform motion. Did you get it?
Here's a drastic example of the law of inertia. In December of 1954, Colonel John Stapp was strapped into a rocket-powered sled called the Sonic Wind. In just 5 seconds, he was accelerated to a speed of 632 miles per hour, making Colonel Stapp the fastest man on Earth. The rocket sled was then stopped in 1.25 seconds. The force required to decelerate the sled at this rate was equal to the force you would experience by hitting a brick wall at 120 miles per hour. Although Colonel Stapp's body was securely tied to the sled, his eyes tried to obey Newton's first law of motion. Colonel Stapp temporarily lost his sight, and many broken blood vessels resulted in a frightening pair of black eyes. To see pictures of Colonel Stapp after the test, look in the August 1955 issue of National Geographic magazine. The experiments with the Sonic Wind were halted because the risk to sight was too great. Objects in motion, even eyes, do tend to stay in motion.
Imagine this situation. You are sitting in a plane or train or even in a car that is moving uniformly. In other words, at a constant speed in a straight line. What will happen if you toss a coin straight up? Will you and the vehicle move out from under it so the coin slams into the back of the car or plane or train? No. That's because objects in motion stay in motion. The coin is already moving horizontally with the vehicle. So, as it goes up and down, it also continues to move forward. It will come straight back down into your hand. Now, this kind of smooth ride was not common in Galileo's days, so it was hard for people to imagine such a situation. So, Galileo asked them to think about this.
Galileo asked people to picture a boat moving smoothly through the water. If a sailor dropped a ball from the top of a mast, the sailor would see the ball fall straight down and land on the deck at the foot of the mast. To the sailor, whose frame of reference is the ship, the mast is standing still, and it would be logical for the ball to fall straight down. But to the people on the shore, the ship and its mast are moving. They would see the ball moving forward as it falls. Galileo explained that since the ball was already in horizontal motion with the boat, it would continue to move forward as it falls.
With the line behind me to use as your frame of reference, I'll hold a ball up like this and move uniformly from left to right. When I reach the line, I'll drop the ball. Watch what happens. You can see that the ball continues to move forward as it falls. It was already in horizontal motion, and objects in motion stay in motion. Now we'll do something a little different. This time, the ball will be at rest at this position. When I reach it, I'll simply knock it down. What do you expect to happen? Tell your teacher. Because the ball was not initially moving with me, it had no horizontal motion. So when it was released, it fell straight down. Is that what you predicted? I hope so. So far, we've talked about objects at rest staying at rest, and objects in motion staying in uniform motion. Now, let's talk about changing an object's motion. What is the one word we use for change in motion? Tell your teacher. If you said acceleration, you learned something in the last unit. Let's go over some examples of accelerated motion. The most obvious example of accelerated motion is an object speeding up. Then there's slowing down, which we call decelerating, but is just another form of acceleration. Starting from rest is also a form of acceleration, and so is stopping. Changing direction is acceleration also. And that includes motion in a circle, like revolving. So, it all boils down to this. The inertia of the object in each example resists the change in motion, and a net force must be exerted on each object to produce the change. Inertia resists acceleration, and a net force causes it. Newton's first law describes an object's motion when no net force is acting on it. The logical next step is to describe an object's motion when there is a net force acting on it. That brings us to Newton's second law of motion.
Newton's second law of motion is often called the law of acceleration. When a net force is applied to an object, the object will accelerate in the direction of that force.
No, an object does not always move in the direction of the net force acting on it. That's not what Newton's second law says. The object's motion changes in the direction of the net force acting on it. Look at this example. The ball is moving upward, so we'll call that the positive direction. But the net force acting on the ball is the force of gravity, or the ball's weight, and that's in a downward direction. Newton's second law says that the object will accelerate or change its motion in the direction of the net force. So the ball will accelerate downward. How does it move up and accelerate down? The answer is that the ball slows down or decelerates at 9.80 meters per second squared. Slowing down is accelerating in the opposite direction of the motion. There's more to Newton's second law of motion, but we'll need to do an experiment to discover it. Let's save that for the next program. But now it's time to show what you know. Jot down your answers only. Your local teacher will go over the answers with you.
Question number 1 is, a toy car is rolled across the floor and slowly comes to a stop. Aristotle would say that this was because A, it seeks its natural state, which is at rest. B, its inertia causes it to stop moving. C, friction causes it to slow down.
Question number 2 is, how would Galileo and Newton answer question number 1? A, it seeks its natural state, which is at rest. B, its inertia causes it to stop moving. C. Friction causes it to slow down.
Question number 3 is, the best measure of an object's inertia is its A. Volume, B. Weight, C. Mass.
Question number 4 is, what is the net force needed to keep a rocket moving uniformly in space? A. 9.8 newtons. B. 0 newtons. C. The weight of the rocket.
Question number 5 is, when a bus moves forward suddenly, a passenger standing in the aisle, A. feels like she is falling backwards, B. actually remains at rest while the bus accelerates forward, C. obeys Newton's law of inertia, D. all of these.
That's it for your introduction to Newton's laws of motion. But we're not through with the old guy yet. Next time, we'll find out why Newton knew that a feather and a hammer fall at the same rate on the moon. And this was almost 250 years before humans actually walked on the moon. What? Glad it was an apple rather than this thing that conked him on the head. Until next time, may the net force be with you.